Okay, ladies and gentlemen, I have the honor to represent the entire Mars 18 team from the University of Stuttgart. And I'm proud that after almost 1 year of work, and definitely more than 1,000 emails, we can present you our concept for a Mars flyby mission in the year 2018. So why do we want to do this? We want to pave the way for human exploration and utilization to Mars in the year 2018. It is a stepping stone to manned interplanetary landing missions, and it can reignite the worldwide interest in space exploration, and thus serve as a platform for international, peaceful collaboration and competition. Furthermore, we can facilitate the development of more advanced technologies for future missions. Our concept shows how this is possible with a budget of $5.2 billion, 2 launches bringing 63 tons into a low Earth orbit, requirements of 3,300 watts of electrical power, 34 cubic meters of volume, and a minimized risk of short and long-term harm to the crew. Before I get started, I will give you a short overview of our mission with this video. Oh, the sound turned on. So after showing you some pretty pictures and some epic music, I will now present you some facts too. And of course the first question is, how do we get off the planet? And what do we do with the human aspect of the mission? Our plan is to use a Falcon Heavy with an asymmetric payload fairing to get our propulsion module into orbit, as well as an Atlas V 441 from the United Launch Alliance to carry our manned mass transfer vehicle into orbit. The man rating of the Atlas V is expected by 2017 as part of the Commercial Crew Development Program, and it is a reliable launcher, thus ensuring the safety of the crew. Having only 2 launches also heavily reduces the complexity and the cost of the mission. Our launch manifest has allowed us to minimize the stay in a low Earth orbit, and our manned vehicle is launched after our propulsion module to increase safety for the crew. We have only 2 automated rendezvous maneuvers in a low Earth orbit, one of which, as you can see next to the Atlas V, is close to an Apollo-style configuration change. Our propulsion module consists of 2 modified Delta IV 4-meter-second stages, which is a reliable upper stage and has currently the highest ISP available. It will be carried with a Falcon Heavy and an asymmetric payload fairing to fit the module. An asymmetric payload fairing is currently under development, and it has the same load factors as a normal payload fairing with only an increase of 30% in mass. And their flight qualification is expected to be in 2015 to 2017. The configuration change will happen with telescope beams, and boil-off in low Earth orbit is considered, so that the entire mission does not require any extravehicular activities or refueling. The trajectory is very close to the initial Inspiration Mars trajectory, with a TMI requirement of 4.8 kilometers per second as the delta V, a Mars flyby where we'll have a gravity assist to achieve a free return trajectory, which is also safer, and a return to Earth with 14.2 kilometers per second when we hit the atmosphere after 501 days. Considering the human factors, after we chose the suitable candidates, one of the most important factors to stabilize them mentally is to synchronize the circadian system, which can be achieved by a regular plan each day and by having controlled day and night cycles. It is also important to provide the astronauts with intimacy and privacy. And we use audiovisual stimulation to positively influence factors like sleep, mood, and concentration. Every astronaut is also allowed to carry 3 kilograms of personal items as to create a more endearing environment in the spacecraft. To prevent psychological disorders, the astronauts have to fulfill monitoring surveys on a regular basis and will be provided with individual challenging tasks like scientific work and, for example, language learning on board of the spacecraft. Another aspect of having humans on board a spacecraft is to ensure their physical health, which can be achieved with a combination of workout and nutrition. As to workout, we propose a reduced version of an iRed, basically, which consists of bungee cords with an additional ergometer and a vibrating plate. This equipment amounts to a total of 150 kilograms, reduced volume compared to the iRed and RRed, with about similar efficiency. In addition, the nutrition will be enriched with bisphosphonate, which is an anti-resorptive drug. Each astronaut has to train 1.5 hours a day, so that the musculoskeletal decline is not too heavy when returning to Earth. We'll now give you a brief overview over all of our spacecraft subsystems. First of all, our structure consists of a modified tracking with a modified trunk, as well as a Cygnus-enhanced module. We found that this configuration fulfills our requirements on mass and volume best, and Dragon will be available and man-rated at the time that we will try to launch. As you can see in the system layout, we don't require any umbilical cables, and we don't have any external piping, which means we don't need any extravehicular activities to maintain most of the subsystems during flight. Talking about maintaining, we also propose to bring along a metallic 3D printer for smaller spare parts. As you can see, we propose rather extensive modifications on the trunk, but this can be achieved in the time that we have until 2018, and it would also make the trunk viable for future missions. Our electrical power system consists of 4 ultraflex solar arrays, which are currently under development also for the Cygnus-enhanced spacecraft, and lithium-ion batteries for power storage when we have a blackout, which will be flight-proven by 2018 on the ISS. As you can see in the diagram, this puts us in line with modern spacecraft like the Orion capsule and the ATV. For our live control system, instead of using a conventional closed loop, we decided to use synergies to achieve 100% waste reusage. Thus, we can maximize the subsystem TRL. We can increase the reliability. We have to use less low TRL technologies and reduce the overall weight. Key technologies here are the so-called VP-car, which is able to regain water from organic waste, and the waste compactor, which will also produce tiles for our radiation protection system, polyethylene tiles, that is. So that is the first synergy there. The second synergy is that our waste gases like methane and carbon dioxide will be used in the attitude and orbit control system for the resistor jets. As I just mentioned, our attitude orbit control system consists of a flight-proven sensor actuator suite with additional resistor jets, which utilize the waste gas from the life support system, and we propose to use a model predictive control algorithm, which, as you can see in the diagram, minimizes the control effort, which translates directly into fuel savings, into mass savings of the overall spacecraft. And a similar procedure has already been used on the so-called Prisma formation flight project by the Swedish Space Agency. Our main radiation protection concept is to increase the overall amount of water and polyethylene by which the astronauts are surrounded. Looking at the diagram on the left, you can see that this puts us in the passive shielding approach, and with a considerable higher TRL than active shielding approaches, but a pretty high efficiency when compared directly. This the layout, the main protection using these passive approaches is the distribution of our payload, the polyethylene tiles that we produce with the waste compactor, and the polyethylene tanks that the life support system will use. Distributing them correctly in the Cygnus capsule, we achieve a shielding that is similar to the Trans-Hab module that was developed by NASA. And on the right side, you can see that we also have a so-called sheltering made out of polyethylene, which reinforces less shielded paths within the spacecraft. Thus, if we have a solar particle event, even if we're not able to bring the ship in the correct position in time, we will have a storm shelter inside of the Cygnus capsule for the astronauts. Using simulations with SPENWIS, we determined that the overall dose during the mission will not exceed 0.56 sievert, which means that the risk for cancer does not increase by less than 1%. Our thermal control system had to be flexible and robust, as we have two extreme cases in Earth orbit and at the Mars flyby. We have 4 panels which can be deployed individually. We use carbon-carbon radiators to reduce the overall mass. And we use only non-toxic fluids in the inner and outer loop, which would allow the astronauts to at least maintain the TCS to a certain degree from inside the spacecraft without being worried. Moreover, the TCS uses water from the life support system for the re-entry and aerobrake maneuver as a heat sink to avoid overheating of the capsule. Talking about re-entry, our thermal protection system consists of a heat shield made out of the often already quoted PKX material, which is cheap, it is flight proven, and it withstands multiple heat flux peaks, which is required if we have the skipping re-entry. Making a conservative estimate, we came up with a total weight for the heat shield of 600 kilograms, which, as you can see in the diagram, makes our spacecraft basically high performance, considering the total heat load and the mass fraction. For the return to the ground, we have a parachute and water recovery system, and we consider the micrometeorite protection consisting of an aluminum shield with a jettison mechanism, so that there will be no damage during the mission. Our communication system consists of 2 high-gain parabolic antennas, as well as 2 low-gain backup antennas in the X and S band. We will use mostly 50-meter ground stations, as this would lower the costs and allow a permanent link to the spacecraft, which is especially important, not only considering the safety of the astronauts, but also their mental stability, as peer support can play a major role here. For about 150 days, with 50-meter antennas, the data rate will drop below 200 kilobits per second. But this can be mitigated by using larger ground antennas in the Deep Space Network or the STRAC network. Also related to this is one of our proposed experiments. The laser communication system, which has already been tested in a lunar orbit, could here be tested over a longer distance as a backup system and possibly to transmit more data from the spacecraft, for example from cameras, but also just to transmit more messages. Another proposed experiment is the Alpha photobioreactor to further investigate the use as a future deep space regenerative resource. We overall allocated 300 kilograms to scientific payload, And we assume that the power and volume is largely covered by our margins. As you can see in our budget, these are basically the numbers that I mentioned in the beginning. We have an overall mass of 63 tons. 48 tons is the propulsion module, 15 tons is our spacecraft. And we have an overall system margin of 20%, as well as 5 to 20% margins for single elements for modifications and development. We'll now talk about the return to Earth and, of course, some programmatic issues. When looking at the return to Earth, we constrained the maximum load factors to 8G and the time for re-entry below 14 hours. This resulted in the worst case of 3 skips and a best case of 2 skips with a re-entry. We found out that the perigee is of other importance, considering the bank angle range during re-entry. Because it is such a high precision maneuver, mistakes or failure to monitor the atmospheric composition correctly can just shoot the spacecraft out at the atmosphere into outer space again, or make it re-enter directly, which would make the spacecraft melt. So we choose the perigee in the first skip, the diagram on the right is the first skip, around 63 kilometers, where we have the largest bank angle range to ensure that we have some kind of flexibility during re-entry. In our cost estimate, we used a combination of commercial and governmental cost models as well as analogies and build-up. We included a 20% overall margin, we included development costs, and we came up with a total number of about $4.2 billion for the entire mission. In the scheduling approach, we assume 3 to 6 months for procurement and scaling of items, as well as realistic estimates for the development of critical and more complicated, like the life support systems. And we actually found out that it is possible to test the entire life support system for 500 days before launch, which is very important since we want to know that our astronauts can survive. In the risk identification, we considered different technological and human-related risks. And we saw that most of them can be mitigated with appropriate measures. But one risk that prevails, that could happen, and that is absolutely critical, is a failure due to scheduling. And in our opinion, this can only be avoided by building up strong public support and by having transparent and solid finances as to not to lose the public support in the execution of the program. So what are our conclusions? A mission to Mars in 2018 is possible with strong public support, as we just mentioned. Another proposed launch window in 2021, however, would allow the development of advanced habitats. In our concept, we have about 15.7 cubic meters of living space, which is above the critical tolerable limit as proposed by NASA. But launching in 2021, we could develop more advanced habitats like inflatables or like the Nautilus at artificial G-ring. And we could also take more advanced training devices. The already mentioned asymmetric payload fairing, however, is another step to actually bringing such large volumes into low Earth orbit. So our entire concept revolves around integrating this mission into existing programs like the commercial crew launch, and about taking technologies as a stepping stone for future missions. Thank you very much for your attention.
Your launch configuration with the two Delta, upper stages side by side, it's kind of unique. Did you look at it instead redistributing things to basically have those split between the launches, perhaps do them both on heavies, and then split your payloads as well?
So one of the, so we have our specialist here, so you can
Yes,
answer
we
that
thought
question.
about that, but actually we took this option for one docking maneuver less, because 3 docking maneuvers would cause a much more complicated mission complexity and increase the risk of any failures. So we decided for this option to decrease the whole mission complexity. So we thought 2 launches would be the best option.
And also, we wanted to separate the propulsion module from the habitat where the astronauts actually are, because this is launched first, and so if there are any problems, the mission could still be delayed to ensure the safety of the astronauts.
Was there any example of this kind of mechanism you've seen used before?
No.
Gave you some confidence?
No.
Okay.
What I actually forgot to say is that all of our technologies are above TRL 6. We made sure of that in our estimates, except for the asymmetric payload fairing, which has a TRL of around 4, and the telescope beam configuration.
How did you account for that then in your mass and cost? Did you do something to...
Well, we said that we have a system-wide margin, but also the element margins. And so basically, we put the highest margins, the element-wise highest margins on systems like this, and also in the cost estimate. I mean, for the different cost models, the coefficients. So we always took for this kind of systems the worst kind of coefficients that we could get.
Okay, good.
Did you think about that relative to making a larger stage? So you're trying to use off-the-shelf stages.
Yes.
An alternative would be, say, use the same engine, however, make a larger structure, larger tank.
Yes, but this would cause huge development, which would be necessary for developing a completely new upper stage. This would cause new qualification of this upper stage and new tests of these upper stages. And these stages are used for most of the times and for many Mars missions from the NASA, and is was really reliable. So we decided that this option would be the most simple and the most safe structure.
Could you talk about how you got to that very aggressive heat shield mass ratio with a shallow back angle and quite a fast reentry?
I don't understand the question. But what I'm asking.
Your ratio of your TPS mass fraction is quite low.
Yes.
And you've got a very shallow back shell angle with the Dragon. So can you tell me how you got to that TPS mass fraction being so low?
Yeah.
Okay, so this graph also compares past re-entry systems. And I mean, we are using a re-entry with 2 atmospheric passes, so basically aero braking, and also very modern layer PKX. So that's why I guess we're overperforming.
But I think what you also mean is the estimates that we made in the design of the heat shield. Yeah, so
in these, we were really conservative with the estimations, and we used most of the time Apollo references for doing that. So the basic informations were done with NASA scheme, which is called the virtual ablation method. And after calculating this, we came out with these masses and mass fraction.
I guess, somewhat related to David's question, were you looking primarily at the four-body heat shield, or did you also look at the aft body? Did you look at the primary, were you just looking at the primary main heat shield, or also the aft part of it?
Most of the time, so the most thing is the main heat shield, and also the back shield, right? Yeah, we can also consider that.
Any further questions? All right. Thank you very much.